All right, so for our next example, we are given a graph of f of x, and we are not given any algebraic description of it. So we're going to be doing a lot of the same stuff, but this time from a graphical perspective. So there's a few parts to this problem. Here's our graph of y equals f of x, and we are looking for a few things. The partition numbers of f prime. We are looking for critical values of f. We are looking for intervals where f is either increasing or decreasing. And then finally, we're going to find any local extrema of f as well as where they occur. And we'll specify which type, whether local maximum or local minimum. So starting with part A, we're looking for partition numbers. Remember, partition numbers are those numbers where either the derivative of f is equal to 0 or the derivative fails to exist. And remember, we are not looking at the graph of f prime. We're not looking at the graph of the derivative. We're looking at the graph of f of x. So we have to use f of x, specifically the graph of f of x, to extract information about its derivative. So the partition numbers, again, if I'm looking for a place where the derivative fails to exist, then I'm looking specifically for places where the graph is discontinuous, and I don't see anywhere where this graph is discontinuous, or where we have corners or cusps in the graph. And I'm also not seeing that in this graph. So I don't think for our partition numbers, we're going to find any of those where the derivative of f is non-existent. So instead, we're going to look specifically for those places where the derivative is equal to 0. And remember, the key for that is to look for horizontal tangent lines. Those are going to occur typically at the tops of these little hills or the bottoms of these little valleys, or they can occur in places where we get something that looks kind of like a cubic function, but I'm not seeing any of those. So right now, all I can see as far as the horizontal tangents are these 4 values here. Okay, so the x values corresponding to those points where those horizontal tangents occur are going to be the partition numbers for my graph. So for f prime, I should say. So the partition numbers, let's say partition numbers, are x equals, so I have -8, that's one of them, -3, 2, and 5. Those are the 4 partition numbers that I am seeing for this graph. Next up, B. What are the critical values of f? Remember, critical values and partition numbers are almost the same concept. There's only one small difference, and that's that the critical values of a function f are anywhere where the derivative of f is equal to 0, so that's the same for partition numbers, or where the function is not differentiable, but those values of x for which it's still differentiable would have to be in the domain of f to be considered a critical value, whereas that's not necessary for partition numbers. However, as we already said in part A, there were no places on this graph where f appeared to be non-differentiable. So what that means is that we're really just looking for where the derivative of f is equal to 0. And we've already identified all x values at which that occurs. So in this case, the critical values of our function are the exact same as the partition numbers for f prime. It's x equals -8, -3, 2, and 5. So no real additional work to do there. Next step, find the intervals where f is increasing or decreasing, and then, well, we'll get to the extrema after that. So once you have identified those partition numbers, we just look at the intervals that they create. So I can see that from basically -infinity, because I don't really know what's going on past -10. We'll assume that this continues to just go downhill as we move to the left. I see that my function is actually increasing all the way up to -8. Then we have that partition number where the derivative would switch sign. We go to decreasing. And then I'm increasing from -3 to 2. I can see my graph is going uphill. And then we decrease from that partition number, x equals 2, to the next one, x equals 5. And then we go back to increasing again, and we go off screen. So we're going to assume that that's going to positive infinity. So summarizing that, we are increasing on the following intervals. So the first one was -infinity to -8. And remember, we use open intervals for this because the end points are not included in these intervals. Then we don't see an increasing trend again until here. That goes from -3 to +2. And then the next time we see an increasing trend is here from 5 onwards, so from 5 to infinity. We're decreasing on the intervals that we did not write down yet. So decreasing on this interval here, so that goes from -8 to -3. And then again here from 2 to 5. Okay, and again, normally we would be looking at the algebraic representation of a function and then using the first derivative along with some analysis of that to get these intervals. But from a graph, we can just visually see what's going on without having to do that extra work. Next up, and finally, is the local extrema part of this question. We want to find all local extrema. And again, those local extrema only ever occur at critical values. And sometimes you get a critical value at which there is no local extrema. We have seen examples of that. But in this case, every critical value seems to give me either a local maximum or a local minimum. So looking at the graph itself, I have a local max of what? So I have one here. Notice it's a maximum because in this little interval here, it's the highest point. And remember, the maximum itself is the y-coordinate of that point. It's the 3. So I could say local maximum of 3 at x equals -8. Remember, the at part is the x value of that point. And then we have another local maximum over here. It's the top of a hill. That is a local maximum of 1 at x equals 2. Okay? So those are the two local maximum values that I'm seeing. Then we have local minimum values at these two valley bottoms here. So this one I would say has a local minimum of -2 at x equals -3. And of this one here has a local minimum of 0 at x equals 5. Okay, so we've identified all of the local extrema as well as where they occur, and then by stating local max or local min, we have also specified the type. That's everything that we were asked for in part D of this problem. Okay, let's take a look at another one where we have a graph to work with, but this time I'm looking at the graph of f prime, not f. So I don't know what the graph of the original function f of x looks like, but I do know what the graph of its derivative looks like, which is what we have here. So we have to shift our thinking over to the fact that we're looking at the derivative and not the original graph itself. So we're going to be answering basically the same set of questions, but from this different perspective now. So the partition numbers of f prime. What are the partition numbers of f prime? Well, starting with those, remember, those are the places where either f prime is equal to 0 or f prime fails to exist. Now, looking at my graph, I have a few places where one or the other of those occur. So first of all, f prime is equal to 0 wherever its graph crosses the x-axis. Notice we're no longer looking for those hilltops and valley bottoms anymore because we are not looking at the graph of f of x. We're looking at the graph of f prime. F prime is equal to 0 anywhere I have an x-intercept. So my partition numbers will include x equals 0 because I have a point here at 0, 0. And remember, it's not only the places where the derivative is equal to 0, it's also wherever the derivative is non-existent. So I have these holes in my graph here where x is equal to 2, and I don't see any point anywhere where x is equal to 2, just a couple of holes. So to me, that would suggest that the derivative does not exist at x equals 2. Now, it's not just the fact that there's a discontinuity here. You can have a discontinuity, but still have f prime existing there, and it would require a point either here or somewhere else. It's just the fact that there's no point at x equals 2. So partition number at x equals 2. I see the same thing happening here at x equals 7. There's a hole there and a hole there. Okay? We have a different type of discontinuity here where x is equal to 11. It looks like we have a vertical asymptote here. Being a discontinuity, that would mean that the derivative does not exist there, or not just that it's a discontinuity, but a vertical asymptote. There's no point anywhere along x equals 11, so I would say that that's also a partition number. And then again, we see another place where the graph crosses the x-axis, which remember that's where the derivative would equal 0, and that happens at x equals 12. So 5 partition numbers, okay? Now, of these partition numbers, we will try to get some critical values, okay? So from what I'm seeing here, the critical values of f are going to be those places where we have, where f is defined, but the derivative, sorry, let me say that again. The critical values are the same thing as the partition numbers in the sense that anywhere where f prime is equal to 0, we have a critical value. And then like partition numbers, we're also looking for places where the graph is, where f prime is undefined, but f is defined. So that's what makes it different from partition numbers. Where we're going to get the important information from that is up here. It states in the description of the problem that f, which remember we're not seeing, is continuous on its domain of negative infinity to 7, union 7 to infinity. The fact that it's continuous there, and that's what its domain is telling me that this function is defined everywhere except at 7. That's the one real number that doesn't exist here. So when I go and I find my critical values, remember, the critical values are the same things as the partition numbers, except we would not include any numbers that are not in the domain of f. And the only number that's not in the domain of f is that 7. So x is equal to 0, 2, not 7, but 11 and 12. Okay? So we have almost the same list of values there. C, on what intervals is f increasing or decreasing? We use the partition numbers to determine those intervals. And again, what we're looking for is a sign change in f prime. F prime is positive anywhere where its graph is above the x-axis, because that's all the positive y values. It's negative anywhere f prime is below the x-axis, because that's where all those y values are negative. So really that's what we're looking for. Is the graph above or is it below the x-axis? And we're using these partition numbers to separate out those intervals. So let's see, increasing on. Which intervals is our graph increasing on? Well, I see that f prime is positive from negative infinity all the way up to 0 because we're above the x-axis that whole time. And 0 was one of my partition numbers, so it's increasing on negative infinity to 0. And then it's decreasing from 0 to 2. So maybe I'll do both parts at the same time. Decreasing on, okay? So it's decreasing from 0 to 2, and that's between two partition numbers, so I can list that here. And then it's increasing from 2 to 7 because, again, notice that our graph is positive that whole time. So from 2 to 7, like that. And then my graph is negative from 7 to 11, and then still negative from 11 to 12. So we know that it's decreasing on 7 to 11, and then from 11 to 12 as well. And then from 12 all the way up through infinity, my graph is above the x-axis, which indicates a positive derivative, which means f is increasing. So I would say from 12 to infinity right here. Okay. Finally, I need x values where local extrema of f occur. Notice we no longer need to find the actual values of those local max or mins. What we need is just the x values. And the reason why that's the case is because we don't have the graph of f of x to look at. So we can determine where those max and mins are occurring, but we're not able to see where they are relative to the y-axis anymore. So just looking for the x values and what type of extrema we're dealing with. So first of all, where do we have any local max values? And then we'll also identify local min values. Local min. At where? Okay, so I'm gonna have to kind of go up and down for this. But remember, from the first derivative test, if the derivative of our function switches sign, then we're going to have either a local maximum or a local minimum value, and that can only occur at critical values. So we only have 4 values here to verify this for. Starting with x equals 0, I can see that my derivative switches from being positive to negative once I go through x equals 0. And remember, positive to negative means I have a local maximum because I'm going from increasing to decreasing. That's from my first derivative test. So there is a local max at x equals 0. What about at x equals 2? That's another critical value. Sorry, it's down here. So at x equals 2, we have our graph where it's a negative, but then it switches to being positive once I pass through x equals 2. So negative means decreasing, positive derivative means increasing function. So we have a local minimum at x equals 2. What's happening at 7? Well, 7 is a partition number. We don't consider 7. 11, critical values. As I pass through x equals 11, our function is decreasing because I have a negative derivative, but then when I pass through x equals 11, we are still decreasing because my derivative is still below the x-axis. So there is no local extreme value at 11 because there isn't a sign change that occurs in its derivative. But what about at 12? That's our last critical value. We're switching from negative derivative to positive derivative. So decreasing to increasing by the first derivative test, that would be a local minimum value at x equals 12. Okay, so again, the analysis here was a little bit different because, again, we were looking at the graph of f prime and not the graph of f. Let's take a look at one last example. This one will be an application problem. So what we're looking at here is this. A company has a price demand function given by p of x equals 50 e to the negative 0.002 x dollars per item sold. Determine how many items the company must sell so revenue is a maximum. So first of all, is talking about revenue. Remember, revenue, R of x, is equal to x times p of x. And we talked about that last chapter. In this case, that would look like 50x. Notice the x is appearing now. E to the negative 0.002x. Okay? It's asking me to determine where the revenue is a maximum. And this can be determined by using our first derivative test. So the first goal is to find critical values for this function. Critical values are determined by finding its derivative first. So I'm going to find r prime of x. Now that is going to require the product rule because I have 50x times e, this exponential function. So taking the derivative of that first function, 50x, I just have 50 e to the negative 0.002x. And then I take the derivative of this second function times the first function. So notice when we take the derivative of e to the negative 0.002x, we use that generalized exponential rule that we got from that section on the chain rule to basically just bring the negative 0.002 down and multiply it to that 50 right there, which would give me negative 0.1. And then I still have the x because we left that function alone, and the exponential function is still going to look like this. Okay, so that's the derivative of our function, r prime. So next what I want to do is figure out where any critical values occur. Now this function is composed of polynomials and exponential functions, both of which are defined everywhere. So I'm not going to get any critical numbers where r prime fails to exist. I'm only going to get those where it's equal to 0. We're going to set that equal to 0 and attempt to solve it. So to do that, what I'm going to do is factor this exponential out. So I have e to the negative 0.002x times 50 now minus 0.1x, and that is equal to 0. The exponential function here, no matter what I plug in for x, always comes out to a positive number, so this exponential will never give me a 0. That means if this product of expressions is equal to 0, then 50 minus 0.1x must equal 0. 50 minus 0.1x is equal to 0. This is very straightforward to solve. It takes 2 steps, very, very easy. I get x equals 500 as a result, okay? So x equals 500. That's great. Now let's see what we can do with that. So remember, this is a critical value. We only ended up with one critical value for this whole thing. And at that critical value, we may end up with a local maximum, we may end up with a local minimum, or we may end up with neither. So we have to determine what we're dealing with. That's where we create the sign chart. So I have 500 here. And what I want to do is figure out, is my derivative positive or is it negative in each of these subintervals? And remember, what we do is we choose test points to determine what's going on where. So for example, over here, I can set x equal to 0 because that's less than 500. If I use x equals 0, I can plug it in any version of my derivative that I found. I'm going to have the easiest time, I think, using this factored version. So plugging a 0 in for x here gives me e to the power of 0, which is 1. That's positive. If I plug a 0 in here, this term goes to 0. 50 minus 0 is 50, also positive. I have positive times positive, so f prime is positive on that subinterval. Next, I need to choose a number that's greater than 500, maybe 1,000. Pick whatever number you want, but 1,000 seems like a good one to choose for me. If I plug 1,000 into the x's again in this factored version of my derivative, remember, it really doesn't matter what I plug in for x here because the exponential will always come out positive. If I plug 1,000 in over here, 0.1 times 1,000 is 100. So I have 50 minus 100, which is negative 50. Negative number times a positive number would be a negative number. So I have f prime is negative there. By my first derivative test, because my derivative is positive here, f must be increasing until it hits that critical value. F prime becomes negative after that, so it's decreasing away from that. And I can see that I do have a local maximum there. So this verifies that the company must sell 500 items in order to maximize its revenue. Okay? That's going to wrap things up for section 3.1.